Let's talk about the derivative as a function. Now, in section 2.1, we learned about a derivative at a point x equal to a. So that was written as f prime of a. And we actually had two different definitions. Well, this time what we want to talk about is we want to talk about the derivative of a function. And the output of the derivative of a function is actually going to be a new function. So let's define what that new function is going to be. So what we're going to do is we're going to call our new function, the derivative function, f prime of x. And the way that this is going to be calculated is this is going to be equal to the limit as h goes to 0 of f of x plus h minus f of x divided by h. So what you'll notice is that this is basically the same as the second definition of our derivative at a point. The difference being, instead of using a, we just replace the a with x's. So this is why I told you that the second definition was more desirable than the first definition. While this is the official definition, I sometimes like to rewrite this definition, especially when our f is something that involves like a complex fraction or is itself a fraction. I also like to write it like this. I could rewrite this as the limit as h goes to 0. And we could write this as 1 over h times f of x plus h minus f of x. These two things mean the same thing because dividing by h is the same thing as multiplying by 1 over h. Okay, so we say f is differentiable at a point A if the derivative exists at x equal to a. So that's what we mean when we say it's differentiable at a. All right. A function is going to be differentiable on a set S if the derivative exists at all points in your set S. Okay, so we've done lots of examples where we calculated limits. Now they're going to be framed in the context of calculating the derivative of a function. So we'll look at a bunch of examples together in class. I want to tell you a little bit more about the derivative as a function. We actually have more than one way we could describe the derivative function and the derivative at a point. So we know that one way we could write the derivative function is f prime of x. And this is really called functional notation. So let me write that. This is functional notation. Okay. Another way that we could write it is we could write it as dy over dx. So when we write it like this is almost like saying the change in y over the change in x. In fact, dy is really an infinitesimally small change in the y values. Dx is really an infinitely small change in the x values. So this notation sort of is a slope-like description. And this description is what we call Leibniz notation. It's named after a mathematician that discovered calculus at the same time that Isaac Newton did. Okay, because y is really a description of of f, we sometimes write df dx, right? When we say y is equal to f of x, that means that one thing you could do is you could replace this y with the function name f. So that's another way that we could describe our derivative function. If you wanted to change the name of this function, you would just replace the f with a different letter. So if your function was the position function, you could also write this as ds dx. And actually, if you wanted to change the independent variable from x to t, which is what we usually do when we talk about the position function, we could change that to ds dt. That's probably a better way to say it. In this case, s is the dependent variable, sorry, and t is the independent variable. So these are many different ways that we could describe our derivative, and we're going to use these notations interchangeably. There's another way that we could describe the derivative at a point. So earlier we looked at the derivative function. What about the derivative at a point? Well, when you look at the derivative at a point, again, we know that you could have f prime and then you just plug in that point A. That's one way you could do it. If you wanted to use Leibniz notation, that would be dy dx. We're going to put a vertical line and then put x equal to a there. And this basically means take your derivative dy dx and evaluate it at the point x equal to a. Okay, so this means evaluate dy dx at x equal to a. All right, so these are different ways that we can describe the derivative at a point. Sometimes we want to denote the process of taking a derivative. And when we want to denote the process of taking a derivative, we use something called a differentiation operator. So the differentiation operator is basically denoted d dx. So when you look at the Leibniz notation, you can really think of it as saying, take the derivative d dx of y, or take the derivative d dx of f. All right. So for example, if we want to take the derivative of both sides of the equation y is equal to x squared cosine of x, the way that I would write it, or I could write it is, I could write it as d dx of y equal to d dx of x squared cosine of x. So this d dx is the differentiation operator. It says take the derivative. And this side right here is really what we think of as the actual derivative, right? That's dy dx. All right, everybody. We will work through some examples in class. Take care.